Is being recorded.
Okay, hello everyone to our last online seminar on interval methods and control before the New Year's break. And it's my great pleasure to have Antoine Besset with us, who will present his work in the frame of signal temporal logic verification of cyber-physical systems, which he's currently performing at ENSTA, the Institut Polytechnique de Paris in Palaiseau, France. And before starting his PhD thesis, Antoine received his engineering degree in aerospace engineering and also a double degree in electrical engineering. And now without any further ado, I'll hand over the floor to you, Antoine, to give your talk, as I just mentioned, on signal temporal logic with an introduction and applications to uncertain cyber-physical systems.
Okay, thank you for the presentation. So I'm a second year PhD student under the supervision of Julien Alexandre Di and Joris Tillet. And I'm going to speak about signal temporal logic, so an introduction and then application to uncertain cyber-physical system. Oh, okay, yeah. So let's start with a problem statement. If the drone reaches A, it must reach B within 3 to 5 seconds and avoid the obstacle while reaching ultimately a goal. So in practice, the system is subject to model uncertainties and environmental perturbation. So there is some trivial case where we can verify, like a counterexample where we encounter an obstacle, but there is a more complicated one when we have like a timing related issue. So the key question in this talk is, can it be guaranteed that the system will always perform as designed? So by saying always, it means for every possible trajectory, every admissible initial state, parameters, and disturbances. And actually, we will try to verify nonlinear continuous time system under uncertainties, and they need to satisfy a signal temporal logic specification. So by the end, we will combine reachability analysis and STL monitoring to reason about all trajectory at once. So to present the structure of this talk, first we will have an introduction to signal temporal logic, and then I will explain the problem and changes in verification. And so on, we will introduce a pre-valued STL over reachable sets. And then we will present an approach to efficiently compute a tube to verify a temporal property. And by the end, I will present two practical examples demonstrating the approach. So, signal temporal logic, an introduction. I will use the acronym STL. So STL, it's not the STL5 for my fellow mechanical engineer. It's like for 3D printing, but it's about temporal logic. So here's the definition. Temporal logic allows us to specify behaviors that a system should or should not satisfy with respect to the time. And originally, it was introduced as linear temporal logic for formal verification of computer program. It was introduced by Amir Pnouleni in 1977 in temporal logic for program. And it performs the verification by specifying properties on discrete states. So an LTL formula includes the usual Boolean operator, such as negation, conjunction, and disjunction. And we also have like temporal operators. So there is the next, which means that does the next states verify a specification. The globally, which is on the whole horizon, does a specification solved. Finally, it expresses the existence of a condition, and the until, which is like the more general temporal operators, will allow us to express the globally, the finally, and the sequence in properties. So we evaluate the formula on a trace W and at a discrete instance I, and it works by working from an atomic predicate which is constrained on the system state at an instance. And I will give you like a small example. So we have interval analysis. So it's a nice word. We have a 15 index. And for example, if we have shift R, so does the next letter is R. When we are at E, it's true. And for the next, we don't have any more R after if we indices. So for example, at the 15th position, it's false. We also have the globally A, so does at an instance the whole trace in front of me as only A, so it's always false because we never have full sequence of A until the end. We also have like the finally A, so does it exist in the sequence in front of me an A, and it's true until we finish with the last A of the word analysis. And finally, the until operator. So it expresses that a condition should hold until, from the word, another happens. So like n happens, so we are already true. But if we go to this position, the sixth one, we have A or L until we reach an N. So it's A, L, A, N, and we always have a 1. So to reason about continuous time, we extend to metric temporal logic, and it's an extension to linear temporal logic, which express the constraints in continuous time. So we have all the operators that are enriched with time intervals. For example, we have the globally A. It's the system should hold a constraint for the next 5 seconds. And as we are going toward STL, we want to specify constraints on real valued signals. So we will change the atomic predicates as a constraints on the signals, which is, for example, like x greater or equal than 0. And it allows us to express specifications such as, like always on the next 5 seconds, the signal is greater or equal than 2. And taking a figure from the paper of Oden-Mahler in 2004, we have 2 signals. And looking at the first signal, we can see that the predicate is respected when the sinusoid is greater than 0.7, and we can see that there is a satisfaction that is timely dependent. So the syntax of STL is recursively defined as an atomic predicate, as I explained. The top, the negation of a formula, you have the disjunction of 2, and the main temporal operator, which is until. And from these operators, you have derived one, like the finally, which express the existence of specification that is all at the time between A and B. You have the globally, which means that always on a time interval, my specification should hold. And we also have the conjunction, so the logical end, which is compute from the De Morgan law. And here is some examples specification. So always avoid unsafe region P. It's globally on a time horizon, not P, for example. And another specification would be if we enter region V, we must reach region W within 2 seconds. So it's V implies finally 0 to W. if we look at the first order semantic of the until operator, it's very useful because it lets us express sequential action, conditional states, or ongoing constraints, which are convenient for the exclusivity of timing condition we could have in a system. So let's start with an example of trajectory generation. It was generated using STL-CCP. So we have a simple reach avoid problem, which is expressed as always I'm not encountering the obstacle, and by the end of a time horizon, I should reach a target. So, for example, this is a trajectory generated according to a specification. But we can express like more strict condition, like the puddle carpet example. So in a word, before going inside the formula, it means that if I reach the puddle, I should go to the carpet to wash my feet before going to the target. So it's finally, so does it exist a time where I'm inside the puddle? And if so, I should never reach the target before going to the carpet. And by the end of a time horizon, I should go inside the target. So we have a first trajectory, so we don't go inside the puddle, and we go straight to the target. But another example is we go inside the puddle, so we should go to the carpets within like timing condition and go to the target then. But we are interested in formal verification, so we will focus on monitoring an STL formula. So we have a trajectory S, and the satisfaction signal of a formula phi means that it's true on the time, it's true, the satisfaction signal, when the formula holds at a specific time. And actually, we will use unitary decomposition of those satisfaction signals to deal with temporal operator. So I've put a simple example. When we want to verify the whole formula, which is globally, I'm not in P, and if I reach Q, I should go in W. We start from the leaf, which are the predicates, and we compute satisfaction signals, which we propagate up in the syntax tree of the formula. And here we can see like the decomposition in unitary signals, for example, for W, and the satisfaction signals for the upper formula, Q implies W. So what we need to understand about this decomposition and this structure, it's because it's convenient to handle temporal operators such as until and derived one, because we can use simple operations such as backshifting and interval operation. So we introduced STL, but now I will present the problem and challenges when we want to verify all trajectory at once. So first of all, we consider a system with a unique trajectory defined from an ordinary differential equation of the form y dot equal to a function of the state and the command. But f can be a nonlinear function according to the relationship between the state and the input, for example. And what we want to compute, it's the reachable set at a time. So basically, what is it? It's every possible state or system can reach at a time coming from every possible initial states and command. But actually, as we want to verify continuous time property, we will focus on continuous time enclosure on time intervals, which are steps, and we will use validated numerical integration to deliver a box that over-approximates the true reachable set on this time interval, and the union of all these steps gives our simulation time length. And this piecewise tube, I will refer to like the structure as a tube, preserves the continuous time behavior that is needed to verify an STL formula, because we don't want to have missed events due to sparse sampling. And if we reason about only like discrete states, we go back to linear temporal logic. And in our case, we want to verify like continuous time behavior. So here's an example of a tube. So we have all the states that our system can reach. And on this focus, we can see one box that represents the reachable sets on a time interval indicated by G. So, okay, it's great. We have some over approximation of our system. So if the formula holds, it holds for all trajectory. However, there is sub-problems. First of all, we will see it later. We could have long computation time, like computing the tube. Sometimes when the system is very complicated, it's computationally expensive. And with the formula, we should compute a tube that covers the horizon of the formula. So it's the specified time length needed to verify a property. And it's a condition and approach such as rich set temporal logic. But there is other approach that introduce a false value that allows us to distinguish between like incomplete information and true information, but it may require recomputing the tube with smaller step size. And by saying that we need to recompute the tube with smaller step size, actually we will have like mismatch between the integration step and the STL timing. When we are dealing with temporal operator, we have very precise time interval that we want to verify a property on. But the thing is, for example, when we are using validated numerical integration, we have an adaptive integration step that rely on the dynamic of the system. And the larger these steps are, the faster we can compute the tube. But the state enclosure may be over-approximated in time because we want to cover all the states on a very large time. However, if we want to decrease the integration step, we explode the computational cost. And we can illustrate this problem with this very simple example. So we have two first-order specifications of our system. So we have the first one, which is we should never go on the time interval AB inside the interval V for the system. It's in one dimension, to note. And if we have the wrong time discretization, we can see that we can't verify properly the property here, but the true state enclosure stems a true answer on this proposition. And for the existence, it's the same. Like you can have an indeterminate satisfaction, but using another discretization, you can. So there is two problems. First, there is multiple step size configuration that can satisfy the precision requirement of the verification problem. Here, when we are looking at this example, we might be like, yeah, okay, but we can just discretize between these time intervals, so we will have the information. But the thing is, when we are dealing with temporal logic, the goal is to have a very wide expressivity. So the formula can be arbitrarily nested. And we might, for example, as Richard temporal logic, propose transformation of the formula. But here we want to find iteratively the right integration step. So the second problem I mentioned is the necessary length associated with the formula. We have for every subformula a length that is defined recursively. For example, if we are performing a disjunction between two formula, we should take the maximum length of two. So the length, it's like the time length of information we need to verify the formula. For example, when we have a temporal operator, we take the max one plus the upper bounds of the temporal operator. So we have a time window that we need information on. And the thing is, if we can have some formula, for example, with disjunction, that can be satisfied with a partial tube. I will take a very simple example. My specification is, will I be in my living room in the next 1000 seconds? So I compute incrementally my states, and at 3 seconds, okay, I'm inside my living room. But the thing is, do I really need to compute the other 9,970 seconds that I need for my full formula length? Some can say no. So there are like existing four-valued approach that introduce an additional truth value that distinguish insufficient origin with the completion of the information with it, and inherent ambiguity coming from the states. But the thing is, they may require recomputing the tube with smaller steps before the uncertainty in the satisfaction is resolved. We will see what is this uncertainty later. So yeah, tree-valued STL over reachable sets. It's what will be the focus for the following of the talk. So as I mentioned, when we are dealing with the formula, we start from a predicate. So we define a set predicate with two inclusion tests on it. So either my whole state is included in a set, so my constraint is satisfied for every trajectory at a time. Either it's completely disjoint from this set, so none of the states at a time will respect the constraints. But if we have a crossing, we can't have a proper satisfaction. So what we will do is we will use Boolean intervals and the extension of Boolean operation on Boolean intervals. And the simple interpretation is, if you have 1, it's certainly true that our specification hold. 0, it's certainly false. And 0, 1, it's uncertain. So if we take a step back, now we are reasoning with Boolean intervals. And the thing is, we need to propagate in our syntax tree the satisfaction of every subformula to the root 1. And what we will do, we will perform a decomposition in certain and uncertain unitary parts of every interval satisfaction signals. So a unitary satisfaction signals, a certain one, is means that we have 1, so true satisfaction on a continuous time interval E for the subformula phi, and we have like E satisfaction, unitary satisfaction signal for full interval satisfaction signals. And we also have unitary signals that represent the uncertainty. So we have 2 examples. We have one with a simple Boolean operation, and the second one is the starting of the decomposition to verify a temporal operator. But let's focus on the disjunction at first. So we have a satisfaction, an interval satisfaction signal represented in W, like in blue for W. And the dashed one is for Q. And we just perform actually like intersection of time interval and interval Boolean reasoning on this satisfaction signal. So the result is kind of clear here. But when we are dealing with a temporal operator, we will see that it's a little bit trickier, because we might have a specification like for all times I'm inside this predicate, but maybe at one time I will cross it. But by mitigating the certainty, the whole result can become as one. So there is some subtlety about how we can compute the satisfaction signals of temporal operator. Like on this slide, don't try to understand like every little detail. I will try to explain it in its globality. So we have a semantic to compute the satisfaction signals of the temporal operator until, and it's defined by Mahler in his STL monitoring paper. And the thing is, as we are dealing with uncertainty in your satisfaction signals, we practically need to perform a case disjunction on all of the unitary signals. So when we look at it, what really matters, it's like for a certain case, we can compute the uncertain unitary signals from untimed intervals using just like an intersection of two unitary intervals, a backshifting on time, and again, an intersection on a new unitary intervals, which is like explained here. But, okay, we have an uncertain satisfaction signals, and the uncertainty can arise from either inherent ambiguity from the system, like there is some trajectory of the system that respect the specification, and there are others that are not. And we can have also over-approximation of the reachable tube, which I mentioned because we only compute an enclosure of the true reachable sets. We might have large step size computing all of this enclosure. And also, we can have incomplete information to verify the full formula. So the main idea is to attach marker to each unitary part and propagate them to understand if the uncertainty comes from a spatial uncertainty or from a missing horizon. And actually, if we look at the schematic, we have a tube which is computed, and we have a set predicate x mu, and we want to know if we are inside this set predicate. So in time, we are crossing the set predicate here. So we have a full unitary signals, which is uncertain. Now we don't cross it, and there is a force marker that gives us the information that there is no information because we haven't computed the tube yet. So it's a missing horizon marker. And what we are performing is we are propagating the marker from the predicate level inside the STL syntax tree, so the tree I showed you before, and we look at them at the root formula, so the whole specification of our system. So here are two examples of how this marker can be propagated. So we have like a temporal operation and two subformula phi1 and phi2, and we perform the computation of new unitary signals according to Mahler semantic and case disjunction I presented before. And now we have one unitary signals that has all the marker belonging to the initial one or the other, but this one is certain, so we don't have any markers. And while performing Boolean operation, we have fusion logic. Like, for example, if we have two unitary signals, we just merge all the markers. But if we mitigate the uncertainty, we can just like compute a new unitary signals, which incorporates the uncertainty marker and delays the importance of this marker on the time interval where it's certain. So from an high-level point of view, we will compute an initial reachable tube as fast as we can, for example, and we will evaluate the formula with markers at the very beginning. And when we will look at the satisfaction of our formula, for example, at time 0, if there is a satisfaction of 0, 1, we can do one thing actually. We can bisect in time the corresponding box. So we refine the time intervals, and therefore we refine the state space. And also, if we have transition with a sequence of reachable sets that are causing uncertainty in the satisfaction, we can partially recompute the tube with an higher order method, or then we just update the tube. And if a marker indicates a missing horizon, we can extend the final simulation time by a fixed time step, delta t, and we do another iteration until we have no uncertain satisfaction value. So here's an example. We have a specification which is as follows, with nested temporal operators on kind of all the Boolean operators you can find also. And on the left part, we can see that we have the initial tube that is computed, and we have like gross time stepping enclosure for the transition, because we have like a condition, and if we reach Q, we should reach W in a time intervals. And also we have like big time step, which goes like state over approximation over time. So we have crossing, which can be easily mitigated. And after several iterations, we managed to mitigate most of the uncertainty by recomputing, for example, only the transition here and here, and just like recomputing the right step to mitigate the uncertainty while crossing like the predicate P. So if we look at the satisfaction signal of the formula, at the very beginning, we have a satisfaction which is mostly uncertain in dashed, like the satisfaction in dots, it's always 0, 1. And with iteration, we managed to mitigate most of the uncertainty because we have either 1 or 0. One expert eyes can see that there is always an uncertainty here. But if we look at the horizon of the formula, we have a 3-second horizon. So we have a temporal operator and a verification at 0, for example. We have 1, 2, 1 plus 2, it's 3. And either for this one, it's 1 plus 2, 3. So we have a 3 seconds formula horizon. And when we are at 7 seconds, we need at least a computation until time 10 to verify our specification. So this one is marked as an uncertainty coming from an incomplete horizon. And if we look at the computation time, if we compare 3 approaches, so 2 verification problem, so 2 times, and 2 methods, if we use the uncertainty tracking mechanism at a time when we need higher precision, we can see that we are 7 times faster in the verification problem than using a blind incremental approach, using, for example, a fault-valued one. And as we have seen in the previous slide, we also mitigate the uncertainty, which is very nice. So practical example. We have, for example, an autonomous car with a neural network that is controlling it. And the specification is as follows. The car must reach A within 5 to 7 seconds. Then it must reach B in the next 2 to 4 seconds, while avoiding the middle zone during 8 seconds. So this example is quite tricky because, first of all, we have uncertainties and perturbations that we need to propagate in the whole system. And we have nonlinear dynamic for our car. We have also, in this case, a multi-layer perceptron with 2 hidden layers. And with our approach, like we compute the tube being informed by the satisfaction of the formula. And if we look at this formula, which represents the specification I mentioned, We have a formula length of 11 seconds, but the simulation can stop with this approach at 9.5 seconds while having a guaranteed satisfaction that the system can perform what it is designed to do. And finally, it's a practical implementation. So we have a drone that is evolving in an environment with obstacle, and we want to verify if it's safe to continue the mission. So we will use our sets-based approach to do a forward verification in real time. And if we compare it using a Monte Carlo approach, because we are in sets-based, we are 10 times faster. So it's very efficient. So to conclude, we have a guaranteed satisfaction of the specification, or we have also presented a method to compute parsimoniously the tube. All the tools here are available in Dynabex. And as future work, we want to limit the temporal over-approximation of marker. I don't know if you noticed, but when we are merging unitary signals into a new one, some marker from the right or the left of the unitary signals can have an influence in the final satisfaction, but with a timed uncertainty. So in the first iteration, it's not very important, but if we want to do, for example, set-based trajectory optimization or direct determination of safe initial set, we need to mitigate this over-approximation. And if you are interested in all the works, you can visit my GitHub, and there is a tutorials on all the code to use this implementation. So thank you, and if you have any question, I will be pleased to answer them.
Okay, many thanks, Antoine, for your presentation, and I'm sure there will be some questions. Let's see who wants to start. Just unmute yourself if you want to ask something. If not, I have a list here written down already. Okay, no one has unmuted himself or herself at the moment. Then let's go maybe to your slide 29. The optimization that you're doing at the moment is purely based on playing around with your discretization step size.
Yes.
Yeah, definitely discretization step size has a significant influence on overestimation. I think that's fully clear. But you also have several other hyperparameters of the underlying solver that you have, for example, Dynabex or whatever solver you're using in the background. And those are things like Taylor series expansion order with respect to time or choice of the integrator. Do you have a Taylor method or Runge-Kutta method? Do you use sonotopes for representing the set? Which order of sonotopes you're using? How to perform order reduction, for example, of those sets? Do you also take into consideration this? Because I think you could easily label them in a similar manner. Maybe you need multiple labels. One, for example, you already did optimization in time. And then if time optimization doesn't help anymore, you could also do something else.
Yeah, it's a very, very nice question. First, when we recompute locally the tube, we use an higher order method. So we have less local truncature error, for example. And as you mentioned, we might still have indetermination. So what we are currently working, we are trying to compute the biggest initial set, for example, that allows us to have guaranteed satisfaction of our formula, because it will give us the information that the very first computation we had with uncertainty was also caused because the system is itself, like the system itself has ambiguity. And also, we can verify on the zonotopes without using boxes. But yeah, like the approach stems for like this state representation, because the only things we are indicating is this marker, it's if we are crossing or not. So if the set is the notops and not a box, it's no problem. Like we can reuse this approach. And yeah, you are true. Like if we use the notop representation, we have a tighter over approximation of our reachable sets. So most of the time, we have less indetermination in the satisfaction.
And then maybe immediately a follow-up. If we go, I think it was the slide 27.
Yes.
No, it's not 27. Then I think it's 24. Because
Cool.
I've written down two slide numbers. Yep, this is what I wanted to see.
Yeah.
This generalization of Booleans in the form of Boolean intervals. What came to my mind here is, and you know the presentation that I gave during the SCAN conference, we aimed in our presentation at doing an optimization, for example, of control strategies using such set-based logic or signal temporal logic approaches. And what comes to my mind is it possible to do something like tuning of controller gains in such a way that you're trying to reduce the undetermined behavior? And that would mean, for example, that you add to a cost function for the optimization of a control strategy a term. Yeah, definitely you have to penalize something where the desired behavior is unsatisfied. That means you need a hard constraint. Everything that is false must be excluded.
Yeah.
And what you could penalize is also everything that is uncertain, in the sense that you have this Boolean interval from 0 to 1. You're integrating over the time horizon over which you want to optimize a system behavior. And then what you could try to do is you could try to minimize the interval diameter of this cost function.
Oh, yeah.
Did you think about something like this, or maybe also Julien in some further work?
I don't think so. About trajectory optimization. It's not trajectory optimization, but like when we wanted to determine like the safe initial set, for example, we also use like a robustness metric of our system. So yeah, it's different from your approach because you are like doing control synthesis. But what we performed is we started from a very close, like very small set, and we are trying to measure the reachable sets that is the most likely to cause uncertainty. And we try to tune our system to have, like, for example, the biggest initial state without this closest reachable set reaching an intersection with a predicate. So yeah.
Yeah, I think that's a little bit it is very closely related to what what I just asked. I think it's just treating the problem a little bit in a dual fashion, because in your case you're starting with a small interval, and then I think you're trying to inflate.
Yes,
And the other thing would start with something, okay, you have huge amount of uncertainty, and within that domain you want to optimize and find something that is guaranteed feasible.
Oh, kind of like like a set membership function where you try to measure, for example, the intersection between the predicate and the reachable set, I guess.
Yeah.
So you have like a value between 0 and 1, and you want to like maximize to 1.
Yeah, in this case, you would like to maximize or firstly reduce the interval diameter and then maximize to 1.
Yeah, that's great.
Okay, then let's have a look again at the list of participants. Are there any further questions? Everything has been perfectly clear.
Okay.
If you want to ask
Julien, you have a question or comment.
Yes, I have a question. So, thank you, of course, for this very kind presentation. So you propose a technique to validate or invalidate a trajectory with respect to a formula, but sometimes it's more interesting to obtain some probabilities. For example, you will validate at 80%. And so do you have some ideas to do that?
Yes, it's closely related to what I mentioned earlier. If we are considering the uncertainties stationary, so there is no evolution in time of like an initial perturbation, we can compute like the sets of parameters, and this set of parameters that satisfy our formula can be linked directly to probability of satisfaction. And actually, what we can do is to use like the potential cloud formalism to have enclosure of the distribution of the state at any times, and use the tree-valued approach I proposed to verify with a certain confidence the predicate and then the formula.
Okay, thank you.
Okay, this motivates some further comment, I think. Yeah, definitely this potential cloud approach that Julien worked on, I think, since several years. I think this is definitely something that could be done. I think additionally, or also maybe in a complementary fashion, you could try to consider the approach that Damien No at ENSTA in Brest is doing about interval particle filtering.
Okay, yeah.
Yeah, that's also something that could be done to estimate the probability of satisfaction.
Okay, yeah.
Yeah, he gave recently in the seminar presentation, I think it was, I think 2 months ago or something like that.
Okay, so it's like particle filtering to determine the
Yeah,
probability.
but particle filtering with intervals. That means the particle themselves are interval boxes. And with this, he's then approximating probability distributions in a set-based manner. It has some similarities to the potential clouds.
Yeah, I can add more details about it. Practically, what we are trying to do right now, it's we are changing the approach, because I mentioned earlier that we start with very small sets, and we try to expand them in a way that the formula is still satisfied. And this is why I'm speaking about limiting temporal over approximation of marker. The thing is, when you are looking at a formula, like all the propagation of uncertainty, practically it's either disjunction or conjunction, because the temporal operator, it's disjunction and conjunction of Boolean objects. And what you try to do is when you have an uncertain satisfaction, you can have a list of reachable sets that cause the uncertainty. Like, for example, you can say, like, imagine like, finally, I'm in this room. You have always uncertainty, but maybe there is one reachable set that can be contracted just a little, so you get nice satisfaction. Like, it's an example. And what we are planning to do, in a way, it's doing back propagation from those particular reachable sets that are easy to mitigate, to determine the safe initial sets. And with these safe initial sets, we can deduce a probability of satisfaction if our random variable are stationary in time.
Yep, that looks like a very promising procedure. Further questions from the audience? And if this isn't the case, again, many thanks, Antoine, for your presentation. I would also like to thank all the attendees for participating, not only in this seminar, but also in all the other seminars that we had in the calendar year 2025. And yeah, definitely now after a short Christmas and New Year's break, for which I would like to wish you all the best. We'll see each other again at the beginning of next year, and the first presentation is already scheduled for Friday, the 9th of January. And yeah, we're looking forward to seeing you again soon. Yeah, and all of you, please come safely and happily into the new year.
Thank you, Andreas.